Welcome to this class on financial performance measurement. This is the third class on this topic, and in particular this class will focus on the introduction to dynamics indicators. The difference between dynamic indicators and the static indicators that we have seen in the previous classes is that while static indicators refer to specific moments in time in the life of the project, the dynamic indicators refer to the entire time span of the project. So they consider the whole life of the project in calculating its expected performance. In these classes, we'll analyze several types of dynamic indicators. In particular, today, our outline is based on first introduction to dynamic indicators, and then we'll analyze some concepts that are necessary to better understand how dynamic indicators work. These concepts are time value, cash flows and time representation, compounding growth, and equivalent value. First, we start from the introduction to dynamic indicators. And dynamic indicators are time-dependent performance measurement. As we'll see in these classes, dynamic indicators present three main advantages over static indicators. First of all, as they refer to the whole life of the project, so they take into consideration different periods, they typically smooth out the inaccuracies of the static indicators in some particular years, in the sense that if there are some errors or inaccuracies in the forecast of a particular period of the life of the project, dynamic indicators solve it because, or at least reduce its impact, because they refer to the whole period, and so the error on the single period is less important. Second, they account for the fact that, as we'll see in this class, the value of cash flow depends on their timing. So a cash flow available today will have a different value from a cash flow available in 1 or 2 or 3 years. Third, they consider the whole time span of the life of the project, and so they provide a broader and more complete overview on its performance. So we have two main characteristics of dynamic indicators. First, they are based on time-adjusted cash flows. So in this class, we'll start discussing what we mean for time-adjusted cash flow and how timing of cash flow impacts on their value. Second, as we are saying before, they consider project entire lifespan. So this is the distinctive characteristics of dynamic indicators as compared to static indicators. So in order to understand better the nature and the calculation of dynamic indicators, we've at this point to introduce the concept of time value. Time value means basically that time is an effect on the value of resources that are deployed in the project and that are then paid back to the investors. This is several important implications for the calculation of the performance of a project. First of all, the amounts of money that are available at different moments in time are not comparable. So we cannot just add or subtract cash flows that are available in different moments in the life of the project. So this means that we'll have to introduce some financial operation that makes these cash flows comparable. Second aspect that we'll stress out during these classes is that ceteris paribus investors prefer to receive cash flows earlier than later, or to pay outflow later than earlier, in the sense that it's better to receive inflows at an earlier moment in time. The reason for that is threefold. First of all, the individuals typically prefer immediate consumption as opposed to delayed consumption. So if they're to forego immediate consumption to invest money in a project, they want to be compensated, as we'll discuss, by some kind of interest rate. Second, if the money was available today instead of in 1 year, you could invest this money at some interest rate in the financial market and get in 1 year a higher value. So if you have $1,000 today, in 1 year you will have a higher amount depending on what the interest rate is. So this implies that you will be indifferent between $1,000 today and a higher amount of money in 1 year, as we'll discuss in this class. The third reason why you prefer receiving inflows at earlier moment in time is also because there is inflation that is typically higher than zero. So in presence of inflation, the value of future amount of money is lower. So inflation reduces the value of money over time, and that's why you prefer receiving money earlier than later. So the two first aspects we have discussed, it implies that we'll have to perform some financial operations that are called a discounting, a compounding, that are used to make cash flows available in different moments in time comparable each other. So discounting in particular, as we'll see, allows to calculate the value today or present value of cash flows available in the future, whereas future value, without compounding allows to calculate the future value, so the value in the future or cash flows available at earlier moments in time. So we'll analyze in detail during this class these two financial operations that will allow us to compare the cash flows with the different timing. So as time value is at the basis of dynamic indicators and their calculation, this is the reason why we are introducing this concept now. And if we look at the resources and time value, what is important also to understand is that, as we have discussed in the previous classes, an investment project typically requires some inputs in the beginning of the life of the project, and then will generate some outputs in future timing. So who is investing is expecting from the inputs a rate of return. This means that in the future, the output that will be generated by the project will live to be higher than the inputs, because in this way they will be able to cover not only the inputs themselves, but also to cover the rate of return that the investors expect from this input. So when time passes and the project is generating outputs, typically investors expect that these outputs will be higher than the initial inputs that have been invested in the project, so that these outputs also can include the rate of return they expect from this investment. So in considering the time value, we'll have to consider that in the project there are inputs and outputs that correspond to real and financial flows, because when you invest resources in the project, these financial resources are then transformed into real resources. The project is then generating real outputs that are products and services, and then these real outputs are transformed again into financial flows through the selling prices. And these real and financial flows will be available at different moments in time, and we have to account for these specificities, and in particular to account for the time value of different real and financial flows associated with the projects. Second, it typically happens, as we have just discussed, that the payoff for the project in terms of output is typically realized after the investment, that is the commitment of resources that is typically made at the beginning of the life of the project. So in this case, we have to consider that the output will have a different value because of timing reasons, and we have to account for that through the discounting procedure that we'll see in the next classes. And the third implication of time value that we have discussed and that is important for the calculation of dynamic indicators is that people prefer the payoff sooner rather than later, so that when we combine the cash flows of a project over time, they will have different weights, as we'll see, depending on the moment they become available or have to be paid by the firm or the project. So at this point, we can look in more detail at how cash flows associated with the project are represented over time. So we look at the topic of cash flows and time representation. So in this example, there is a combination of the cash flows of a project over time. So we are assuming a project that is an expected life of 5 years. The project requires immediately, that conventionally, as we have already said, is time 0, an investment of 50. So that's why we have an outflow of 50. Then the project is generating 2 positive inflows at time 1 and time 2, respectively of 15 and 35. Then there is some other outlay here at year 3 that makes the cash flow negative again, it's minus 12. And then we have 2 positive cash flow at year 4 and year 5, or respectively 25 and 40. So the issue here is that all these cash flows that are presented on what is defined as a timeline refer to different moments in time. So they are not comparable. Even though they are expressed in the same currency units, they're not comparable because time value make them different and make them not comparable. So we cannot just calculate the value of the project by summing them up or by subtracting the negative outflow from the positive outflows, because we will be comparing non-homogeneous values. It's like basically adding apples with pears. So it's not possible to do that. So this means that before calculating any dynamic indicator for this project, we have to adjust the value of these cash flows for time, and this is what we'll do in the we start doing in this class, and then we'll go more in depth in the next classes. But so far, it's very important to remind that when you have this cash flow structure over time, you cannot do any kind of operations like subtraction or addition until you have adjusted this cash flow for the different timing to which they refer. In order to make a step further to understand how the time value affects cash flows, let's consider a very simple situation of a currency unit over time. So assume that today you have $1 available. You have 2 choices as an individual. You can use this $1 for consumption. In this case, the dollar is not available anymore by definition. Or you could decide to forego consumption and instead using this dollar to invest in some project. Why should you do that? So why should you forego actual consumption and invest in some kind of project? Well, because you expect some kind of remuneration on this investment. So let's assume that you are investing in a project that is guaranteeing a rate of return of R on the amount of money you are investing at the present moment. So this means that after one period, so in the future, instead of having $1, you will receive $1 times 1 plus the interest rate of the rate of return that this project is guaranteeing to the investor. So this means that if R is sufficient to compensate the individual for not consuming today, the individual should be equivalent between having $1 today and use that for consumption, or having $1 times 1 plus R in one period. So that's why these 2 amounts of money, so $1 today and $1 times 1 plus R, are considered equivalent, because the individual will be indifferent between consuming $1 today or investing $1 in a project that is earning a rate of return on one period equal to R. So R is, in other words, the equilibrium rate that assumes the equivalence between the present value of $1 and the future value of $1 times 1 plus R. So at this point, we can try to understand what happens when instead of analyzing the equivalence over just one period, you analyze the equivalence over different periods in time. And in this case, we have to deal with a financial operation that is called compounding, and so we'll observe in particular compounding growth over time. So here we are considering a simple example of compounding, where basically we have 4 periods. So we have year 1, year 2, year 3, and year 4. And we assume that the individual that has to make the investment decision is $1 to invest today, eventually, if he wants, if he is going to renounce to actual consumption. And then can decide to invest for 1, 2, or 3 years. So it can go from year 1 to year 2, from year 1 to year 3, or from year 1 to year 4. Let's see what happens. So, and let's assume also that in the market, in financial marketplace, there is a rate of return of 10%. So we are assuming R is equal to 10%. Let's see what happens over 1 year. So we start from year 1, and we assume that the potential investor is going to invest his money for 1 year at the market interest rate of 10%. So in 1 year, if he decides to exit the investment, we'll receive an amount of money that is equal to $1 times 1 plus R. So let's see what happens. And this is the result that we have already obtained in the previous slide. So this is, again, the result of the time value of money. And the individual will be indifference between having $1 today, or so at year 1, or having $1 times 1 plus R at year 2. But the individual could decide not to invest just for 1 year, but could decide to invest for more than 1 year. And so let's see what happens if we decide to invest for more than 1 year. Well, the compounding assumption that is typically made in finance is that after 1 year, the investor is not only investing the initial amount of money of $1, but is also investing the return that has been earned during the first period of investment. So in other words, we are not reinvesting only $1 for 1 other year, so from year 2 to year 3, but we are investing the whole amount of money that at this point is available at year 1. So you are not cashing out the return, but you are investing the return along with the initial investment of $1. So this means that when you pass from year 2 to year 3, you will do $1 times 1 plus R. That will be multiplied again for investing 1 year times 1 plus R. So at year 2, we will have $1, that is the initial investment, times 1 plus R, that is that reflects the return that has been earned in the first year, times again 1 plus R, that reflects instead the return that has been earned in the second year, so from year 2 to year 3. So in a more synthetic way, therefore, we can write that at year 2, an investor that has originally invested $1 at year 1, at year 3 will hold an amount of money that is equal to $1 times 1 plus R squared. So in other words, we have a compound capitalization scheme because we are assuming that the return that is earned over time is periodically invested from one period to the other. And this happens also when we pass from year 3 to year 4. So let's assume that instead of investing for 2 years, this individual decides to invest $1 for 3 years, and we maintain the compounding assumption. So what happens is that after 2 years, you will have earned an amount of money that is equal to $1 times 1 plus R squared. He's going to reinvest this money again at an interest rate of 10%. And in this way, in year 3, after 1 more year, you will have a new amount of money that is $1 times 1 plus R squared, that is what he got at the end of year 3, times again 1 plus R. So at the end of year 3, we can write this amount of money as $1 times 1 plus R raised to 3. So as you can see, over time, the initial investment increases with an exponential law because of the compounding assumptions that implies the investment also of the return that have been earned in the previous periods. So here we can see a numerical example that corresponds to the general law that we have just discussed. So you invest $1 at year 1. After 1 year, you will have earned the 10% on this $1, so we will get $1.10. At this point, according to the compounding assumption, you are going to reinvest for 1 year not only $1, but $1.10, so including the 10 cents of return that you have obtained in the first year of investment. So if you invest 1.10 at a 10% interest rate over 1 year, you will get a new value of 1.21 cent, $1.21 at year 3. So now again, according to the compounding law, you can reinvest the whole amount of money, including the 21 cent of return, for 1 more year at a rate of return of 10%, and this brings to the final value at year 4 of 1.331 cents, where this is 33 cents, that this is the product of 1.21 multiplied 1 plus the 10%, that is the rate of return that you earned over the last year. So this operation that we'll see in more detail in the next classes is called compounding, and allows you to transform present value, that is $1, in this particular case, into future values. And we'll tell you what is the results in terms of output of your actual investment. And as you can see, as we had already discussed it in this class, the outputs at future moments in time are higher than the inputs. And this is for the reasons we were mentioning before. That is, that you need higher output than inputs when outputs follow inputs over time, because future outputs have to compensate the investor for the return. So they have not only to cover the initial investment of $1, but they also to cover some expected rate of return that in this case is 10% per year, and that in particular over 3 years becomes equal to 33 cents of dollar. Just a final remark on this specific aspect of compounding growth is that here we are using a constant growth rate, so we are using a constant rate of return of 10%. So we are assuming that this money is capitalized at the same rate of return over time. It could happen, however, that the rate of return is floating, so it depends, it changes year by year, but this will not create any problem. But instead here of having 1 plus R squared, you will have $1 times 1 plus R of the first period. multiplied 1 plus R of the second period. So you will use the same capitalization rule, but simply you cannot just use the same interest rate, but you have to choose a different interest rate for capitalization for each period of the life of your investment. So compounding is a fundamental financial operation that is at the core of the dynamic indicators that we'll analyze in the next classes. So this is a critical point that you should keep in mind for dealing with future topics. So at this point we can conclude this first part of the class by summarizing the main issues of time value, looking at a concept that is the equivalent value, and that allows us to generalize the problem of time adjustment of the value of cash flows. So to understand what we mean exactly for equivalent value, we can look at this slide and to understand the simple example that is reported here. And then in the future classes we'll insist on this problem. So here we have the same case we saw for the compounding growth. So we have an initial investment of $1, and we have a rate of return for one period of 10%. And we assume that if we make an investment, we make this investment at year 1, and we can invest until year 2, year 3, or year 4. So we can invest up to for 3 periods. Here we can see that if I invest $1 in year 1, I will get $1.10 at time 2, $1.20 at year 3, $1.331 at year 4. So here we're just following the rule of compounding. But there is another problem that I could ask. So here I'm asking, what is the money that I get in 1, 2, or 3 years if I invest $1 today? But I could ask another question, that is, if in 3 years I want $1.33, or if in 2 years I want $1.20, how much should I invest today? So this is another question that you could ask in case of financial transactions. So you can see that here the arrows goes in 2 directions, because if the question is how much money I will get in 1, 2, 3 periods, then you follow the blue line and you apply an operation that we saw is defined as compounding. And clearly the value of the money is increasing over time, in the sense that in order to be indifferent between $1 today and a given amount of money in the future, this equivalent amount of money in the future has to increase as time passes by. On the other side, however, you could work in the opposite direction, and you could start from last year and say, okay, I want to accumulate a given capital in 3 years, investing a given amount of money today. So the capital that I want to invest I want to obtain in 3 years is equal to $1.33. And the question is, how much money should I invest today? So, and here you can go back from year 4 to year 3, and then from year 3 to year 2, and then from year 2 to year 1, applying the opposite operation that we applied instead to obtain future values. This operation that here is represented by the orange arrows is defined, as we'll discover in greater detail in the next class, discounting. And this operation of discounting allows you to calculate what is defined as a present value of a future amount of money. That is the value today of an amount of money that is available in a future moment in time. So in other words, when we compounded before $1 for 1 year, we multiplied $1 times 1 plus the rate of return. Now, if you want to calculate the present value, so going in the other direction of the amount of money available at year 2, so the present value at year 1, what you have to do is just divide this amount times 1 plus the rate of return of the 10%, as we'll see then in more formal way in the next class. So when you divide $1.10 divided for 1.1, you get again the $1 that you had invested in year 1. So you are indifferent between holding $1 today or having $1.10 in 1 year. So $1 is equivalent to $1.10 in 1 year. So the value of $1 in year 1 is equivalent to the value of $1.10 in year 2. That means that the investor is indifferent. Then you can extend this work on 2 years. So let's assume that in 2 years you want to have an amount of money that is equal to $1.21. And you want to know how much money you should invest today, and you know that the rate of return for this investment is 10%. So what you do, you first divide $1.21 times 1 plus 10%, that is the rate of return, and you get $1.10. And then you divide again $1.10 times 1 plus the 10% of interest rate, and you get again $1.1. So you're basically dividing $1.21 times 1 plus the rate of return square. So it's exactly the opposite operation that we saw for compounding. So in this way we see that in theory for the investor is the same holding $1 today or getting $1.20 in 2 years. So $1 at year 1 is equivalent to $1.20 at year 3. And finally, we can say we apply the same logic also to the cash flow that is available eventually at year 4. So here you could ask, if I want $1.33 at year 4, how much money should I invest today? So you discount this amount of money for 1 year and you get 1.21. Then you discount that again for 1 year, so you get 1.10. And then you discount that again for 1.10%, and then you have the present value $1. So $1 is the present value of $1.33 in 3 years. On the contrary, you can say that 1.33 years is the future value of $1. And what is important is that $1.33 is the equivalent value at year 4 of $1 available at year 1. And so this is the concept of equivalent value. So all these values that are depicted in these slides are equivalent values over time. So in theory, any investor is indifferent between holding $1 at year 1, $1.1 at year 2, $1.21 at year 3, or $1.33 at year 4. In theory, if R is the rate of return that compensates the investor for receiving the cash flows at a later moment, then the investor should be indifferent between this amount of money available at different moments in time. So why is this important? Well, this is important, as we'll see in the next classes, when we are evaluating a project and we are calculating some dynamic indicator, because typically a project generates cash flows, as we have seen also in a previous slide, in different moments over its life. So it's clear that you cannot just add this value up because these values are not comparable. And so you have to transform each of the cash flows that a project generates at a given moment in time into a present value. So what we'll see is that if you assume that these, for example, are cash flows of a project, through the operation of discounting that we'll analyze in greater detail in the next class, we have to transform all the future cash flows of the project in present values. So we have to transform all these values in values at year 1, following, therefore, the orange arrows and applying what we have defined as discounting operation. Once that we have transformed all the future cash flows of a project into present values, we'll be able to compare them and to do any other operation we need to for the calculation of dynamic criteria. So the concept of equivalent value summarizes what we have said so far in this class about the time value and its impact on the value of resources and financial and real flows, and will be absolutely useful and important to understand what follows. So with this topic, the class of today is concluded, and I remind you that for any additional information you can refer to the website of the course, and I thank you for the attention.